Thank you, Rob. That's very kind. So could we need a second person to help with taking the notes for the meeting. And we need a volunteer, and we're not going to start till we have one. So that's very decisive, isn't it? Thank you, Doug. That's really kind. So welcome everybody. I'm Philip Erdley. Yoshi couldn't make it this time. I suspect he's on remote, so hi to Yoshi and to the other people on Meet Echo. If any of you guys want to say anything at any point, then we can try and get the remote system to work. So we've got two sessions at this one. The second one's on Friday. There are the normal reminders. The blue sheet has started going around. I've only sent one in because it's quite a small room. So hopefully that, could you make sure you keep that meandering around the room, the blue sheet, please. Here's the normal note well. So here's our agenda we've got. So we've got a kind of a session about implementation news and recent experiments that people have done related to the implementation and some work that was done at the hackathon on Sunday. So that should be really interesting, and we've got some news about the iOS implementation, which is also really good. We've then got a little slot on our protocol BIS work that we've been doing, a short update from Alan, and then really a kind of room for discussion about that to try and work out when we think we'll be able to push it through to the ISG. We've then got a longer session about proxies and a related work to proxies. So there's a couple of new drafts there from Olivier and from Vlad. So hopefully there'll be enough time there to get some really good discussion going. And then on Friday, we've got a couple of other interesting talks. So there's one from Marcus about a proposal about how to do robust session establishment, and one from Quentin, which is a proposal for fast subflow creation. So both of those in theory can have some impact on the protocol BIS, I think. I think they're sort of proposals that could impact on it. I didn't think there was time to squeeze all of that stuff into one session, so we'll have a little wrap up at the end, just to at the end of Friday, just to revisit what we think we need to do on the protocol BIS. That's the agenda. Did I forget anybody requested a presentation slot or anything? Everybody happy? Excellent. So just two slides about the working group status. So firstly about completing the BIS, which is our primary goal of the working group, to complete it on the standards track. We need to complete agreement on some of the items that have been raised. We've been working on the last few meetings. We had a talk at a discussion about this at the last meeting in Chicago about our different choices, and we basically decided to wait for implementations to catch up with what the new one or two of the new things that have been added in the BIS document. And because clearly, in order to be on the standards track, we need some implementation to go forward. So hopefully we're getting close, as we will discuss shortly, to being able to then push that on. The other activity we've got going is about multipath TCP proxies. We had a good discussion about this at the last meeting in Chicago. We talked a bit about kind of assumptions and criteria, and we had agreement that minimizing the setup time is an important criteria for any solution in this area. And then we talked a bit about the three high-level solution approaches that people have mentioned. So I think to summarize what happened in that meeting, most people favored one of those, which was called the plain mode draft. However, when we did a more kind of formal look at that on the list, we didn't really find an approach that quotes everyone can live with, which is the definition of consensus, or one of the, it's the definition that we've suggested you use. So from that, we think that more work is needed. So that's why we're having a lot more discussion here at this meeting. And just to alert people, I guess most people here will know about the banana BOF that happened yesterday, which was a working group forming BOF, which my interpretation is that went well, and that there was support for the working group. There was a charter discussed, which was basically people with some wordsmithing to go on. So two of the things that working group should do is firstly determine how local and remote banana boxes, which really means a proxy, can find each other, and secondly to look at specifying a signaling protocol to transfer useful information between the two banana boxes. And then this new working group will say, well, has to work with other IETF working groups. I guess our group being a key example of that, on making sure those things meet their needs. So that's something we're going to have to make sure we have input as a working group or as individuals into that banana activity as it takes off. So that was it as an introduction. Anything anybody wants to have further discussion at this stage? Right, so first on the agenda is Christoph. The PDF's okay, isn't it? Yeah.
Yep. Hello. This is just going to be a short update on the implementations of Mptcp, or some of them and the status of them. Next slide. So I will start with the iOS implementation.
That one's not working.
As most of you know, we are using Mptcp at Apple since now about iOS 7. And we have been using it for Siri. The use case for Siri is mostly because users have a tendency to use Siri while they are walking out of their home. They use it while they are walking. They ask Siri, I don't know, navigate to a certain destination. And so it's very common to basically lose the Wi-Fi connectivity while they are doing this. So as they're losing Wi-Fi, and Siri is just creating a single connection to the server to stream the voice over to the server. And this connection is really critical. If this connection gets dropped or gets closed, then basically Siri doesn't work. Because we would need to recreate a new connection, resend all the traffic again to the server. And so Mptcp is really a perfect use case for Siri. And we have seen over time that we have certain metrics for Siri where we are measuring the performance. And we have one metric that is called the time to first word. That means the time that it takes for the first spoken word to appear on the screen. So it's the time between you speak it until it appears on the screen. And in the 95th percentile, this has been reduced by 20%. and it has been introduced because, well, with Mptcp we are able to choose between Wi-Fi or cell. And in the latest iOS releases, I think since iOS 9, we didn't only use Mptcp for handover, but we also used it for latency reduction by basically whenever we saw that Wi-Fi is being too slow, up to a certain threshold, we basically started using cellular data. And especially in the worst case scenarios, like the 95th percentile, in those cases we saw the improvement of 20% time to first word. And then also the network failures, which is basically the scenario when people are walking outside of their home and when basically Wi-Fi drops. In those cases, we saw a 5% reduction of those failures, which is pretty huge. So it was already very low, but now it's really almost negligible, the number of network failures that we see with Mptcp for Siri specifically. Next slide. So then we have quite a bunch of other multipath technologies in iOS, also already since quite some time now. This one, Wi-Fi Assist, is since iOS 9. And Wi-Fi Assist is very similar. I brought this slide actually just because we also have another presentation coming up that is also very similar to our Wi-Fi Assist, which is basically Wi-Fi Assist is the technology that chooses the interface for the initial subflow. So whenever we create a connection, and Wi-Fi is in a marginal state, that means the signal strength is too low, or some other factors that make iOS believe that Wi-Fi is not good enough. Then we first create a connection on Wi-Fi, and after a certain timeout, we create the connection over cell. And so we take the one that wins this race. And so this is kind of the way that allows us to choose which initial interface to select. And there's a presentation coming up later, Mptcp Rope from T-Mobile, I think, or Deutsche Telekom, and so it's very similar to this. Now, as part of Wi-Fi Assist, we have then added now in iOS 11, we also added Mptcp into it. And so you can go to the next slide. So in iOS 11, we are opening up Mptcp as a public API. So people can start using it, and Mptcp will be steered by Wi-Fi Assist. That means Wi-Fi Assist is basically imposing some limitations on the amount of cellular data that an application can use when Wi-Fi is in a marginal state. So that means basically when Wi-Fi is available, usually people don't expect that an application uses cellular data. But Wi-Fi Assist enables the usage of cellular data even when Wi-Fi is there. And so Wi-Fi Assist is simply putting a cap on the amount of data one can send on cellular when Wi-Fi is available. And Mptcp is just going to be part of this limitation and part of those triggers that send traffic over the cellular data. And so in iOS 11, the opening up of the API will be done in 3 different ways. We use the handover mode, which tries to minimize cellular data usage at all cost, the interactive mode that we are using for Siri, and the aggregation mode that is available for developers only. Next slide. Yep.
Julius Krobacek, just 2 quick questions. So who picks the mode, the user or the developer?
The developer.
Okay. And what does it mean only for developers, since the developer picks in any case? What does it mean in your last point that it's only for developers?
Oh, only in basically the aggregation mode, you can only use it on a developer phone. That means there are developer settings when you have opted in your phone, and then you can enable the aggregation mode. Yeah.
This is Devashish. I have one question, like in Wi-Fi Assist, right? When you were trying to steer towards cellular connection. So now, if there are suppose 2 interfaces on the cellular connection, is there any way to choose them? Which one is the best?
2 interfaces on the cellular connection?
Yeah.
In iOS, we don't support this.
Okay.
Yeah.
Okay.
Well, yeah. At least
there's a possibility there will be 2 interfaces on the cellular connection. So right now, you're not considering anything like that.
We don't have such kind of a use case. Okay. No. So we don't care about that. Okay. Yeah.
Okay.
Yeah.
Thank
you. Do you have use cases where there are 2 interfaces?
We see some use cases where it is possible on the cellular connection there may be 2 interfaces, say 2 IP addresses assigned.
I see. Okay.
Okay.
Yeah, in iOS at the moment we don't have this. So.
Okay. Thank you.
The handover mode. The handover mode, whenever Wi-Fi is available, we only create a connection on the Wi-Fi interface, and we don't use cellular at all. We will only bring up the cellular data if Wi-Fi assist is telling us, wait, Wi-Fi is not good enough, and it has a chance of dropping out. So basically based on the signal strength. And only then we bring up the cellular data and we start sending the cellular if we are getting a retransmissions over Wi-Fi. We recommend the developers to use the handover mode, for example, for long-lived persistent connections. The interactive mode, we use Wi-Fi and cell at the same time. We bring up both together and we schedule the traffic so that we minimize the latency. We still send more traffic over the Wi-Fi interface, but if the latency is a little bit too high on Wi-Fi, we send the traffic on the cellular interface. And that's the mode that we at Apple, we are using it for Siri, and that's the one where we saw the 20% latency reduction for the time to first word. For this particular mode, we recommend to only use it for latency sensitive and low volume flows because they can actually send quite a lot of data on the cellular interface. If an application developer would use this mode and would send too much data, what will happen is basically the Wi-Fi assist will blacklist this application and will prevent it from using Mptcp because we have those limitations that prevent an app to use too much cellular data. And then finally, the aggregation mode that we are exposing only for developers. And the reason why we expose it only for developers is because the aggregation mode will send a lot of data on the cellular link. And we are basically looking for use cases. What use cases do you see, or the developers see, or maybe here in this room see, where this tiny little bit of additional capacity would be worth the cost of sending so much data on cellular link? Because at best, one can only double the capacity of the Wi-Fi link. That's what the maximum one can do. And so the use cases seem to be very narrow and very specialized and not for the general public. So that's why we restricted it for now only for developers. Next slide. Yeah, and so that's all about iOS 11. The API is open, and starting in September, October, we will be sending out the updates for iOS 11 to all customers. And from that moment on, we hope that many application developers will start using it. And I hope that maybe in a year I will be here and be able to show some numbers. We'll see that. Now let's get to the next one, to the Linux implementation. On June 4th, we have released a new Mptcp stable kernel. It's based on version 4.4 of the upstream Linux kernel. The new features in this release were that there were 2 new socket options that allow applications to select the scheduler and the path manager. It has been several years now that we had multiple different schedulers and path managers to use in Linux, and one could choose them with the syscontrol. Now they can also be chosen through a socket option. One use case for Mptcp was where people were setting it up on a home gateway router, for example, and basically doing bonding of multiple interfaces. And they saw that sometimes some subflows were timing out because, for example, the net mapping got lost. And well, when this happened, basically the Linux Mptcp implementation was basically not recovering this subflow. So in this new release, what we added is basically whenever a subflow dies because of timeouts or some other reason, we basically create a new subflow again so that this interface can be used again. So that's also new in the new release. And finally, we also have an Mptcp info API to get more details about the subflows, more details about the state of the Mptcp connection. So that's new on the Linux side, and the implementation is available on the usual website. Yeah, and that's all from my side.
Markus from Deutsche Telekom. I have a question related to the iOS implementation. Do you plan in future to support MPTCP proxies from the iOS itself?
I cannot make any statement about future unreleased products. Sorry.
Okay. Thanks.
We can discuss later.
Okay.
Any more comments or questions? Thanks, that's really interesting, and I hope there are lots of application developers who can now start using it easily via the API in iOS. That's great. Who's up next? Fabian. Is Fabian here? Oh. Which one of these is it? It's that one, isn't it?
Yeah.
I don't know why that's done that. That's weird, but
If you can really try this.
I guess so. I have no idea why it's doing that. It's sort of odd, isn't it? Let's leave it up. That'll do.
Okay. Hello, my name is Fabien Duchesne, and I'm going to give some updates about the address advertisements and the load balancing modification we discussed past the IETFs. Slide, please. So first, an update on the draft that's summarize all the load balancing techniques and the adaptation we can make to Mptcp to make it work with load balancing. So we added a part on the application layer authentication that's been made by Alan. Basically, it decouples the token signaled in the option from the key used for the authentication. So basically, it's an application layer authentication. I think there's some words missing. Here it's okay, but with the figure, probably we have a problem. The next step for this draft is to add some security consideration because we haven't done it yet and it's still important. Next slide, please. So about the address advertisements, we discussed that a lot during IETF 96 and 97. Out of 5 proposals we made, we kept 2, which were the no join flag in the MPK table and the echo flag in the ad address. So what was that? Next slide, please. Just a quick recap of what it was. The no join was basically allowing the load balancer to tell a client, please don't send an MP join on that address because it cannot be used to join. So here we have the example with the green IP that cannot be used to send join. Why? Because the load balancer are hashing most of the time based on the 5 tuple. So if a join tried to join on this address, the server may hash it to another server, and then it will not join. So the no join was just allowing the load balancer to tell the client, please don't join on this address. Next slide, please. The other one was making the ad address reliable. It seemed important in load balancing, and I will show why after. But to make the ad address reliable, basically we use the echo technique. So if you look here, we send an address with the echo bit to 0, meaning it's a real ad address, it's an address advertisement. This one is lost. So without receiving an echo bit to 1, the server will just send the address again until it receives an acknowledgement for that. So the acknowledgement is the echo bit. Next slide, please. So with this, we try to make Mptcp friendlier to load balancer and Anycast. Oh, well, what was the point? The point was we were trying to change slightly Mptcp to make it work with existing load balancer. A lot of done has been work to modify load balancer to make them work with Mptcp. Here we are taking the problem in another way, making, okay, we don't change load balancer because they are there and nobody is going to upgrade them to support Mptcp. And we change Mptcp to make it work with those load balancer. How did we do that? First, we implemented the 2 proposals that I presented just before. So the no join in the reliable address, and we designed path manager that was specific for the load balancing use case. Next slide, please. So what's the general idea of this load balancing path manager. It's actually pretty simple. Say you have to add a public IP address to each server. I know it's sometimes complicated, but this is the drawing we're trying to make. So you add a public IP address that doesn't pass through the load balancer on each server. It could be an IP address or an IPv6, for instance, and this is more realistic. Just a /64 or /56, sorry. So you add a range on the server. So the server can generate IPs and send them to the client. So the server needs to advertise it reliably to the client. Why? Because the idea here is to put the load balancer off path. So when the first subflow is established, the first thing the server will do is advertise the new IP address, the one that's directly connected to the internet, so the client can join this address. Then you put the first subflow in backup mode, so you don't use it. You don't cut it because it can still be useful if the new subflow is cut, but you put basically the load balancer off path. So you expect all of the traffic, or except the 3 or 4 packets that are used for the three-way handshake and the address, to go through on a separate link. With this, the load balancer is kind of only used to match the client and the server. So you use the load balancer that will make the decision you go to this or this server, then you connect directly to the server and you don't use the load balancer connection again. The implication of that is you don't need big hardware to make your load balancer. You don't need a lot of redundability because if the load balancer goes down during the connection continues, and that's the idea. So you could, it's a bit of a stretch, but you could make a load balancer with a Raspberry Pi. For all I know, it would work. Next slide, please. So the pseudocode for the load balancing path manager is pretty simple. It's basically generate a new IP. Why generating a new IP? When you have a range, for some security purpose, there is a discussion about that in a paper that I will present after. But you could say, okay, I will not just add one public IP address on my server because I don't want the whole world to know how to directly connect to my server. So on the fly here, we generate a new IP in an IPv6 range, and we advertise that new IP only to that client. So the client will connect to that one, and when the client disconnects, this IP address is removed and it's not used again. So you generate the IP, you advertise it to the client, and you set the backup mode on the first subflow. Next slide, please. So how does this work with layer 4 load balancer and modified load balancer? On the most left part, you have the traditional NAT setup, where basically all the traffic goes through the load balancer, upstream and downstream. Everything goes through the load balancer. In that case, the load balancer is a bottleneck because all the traffic is going through him. In the middle, you have direct server return. This is heavily used in the industry. Basically, all the traffic coming from the client to the server is going through the load balancer. But the traffic coming from the server to the client is using a dedicated link. This is good when the client downloads files, but when you upload files, the load balancer is still a bottleneck. So this architecture was, we know that there are a lot of DSR, so direct server return in the wild, so we were like, we could use those architecture to make it better with Mptcp. So if you look at the Mptcp figure, the red traffic is the establishment of the first subflow. So the subflow that's used to advertise the address. And then in blue, you have all the traffic that goes both ways between the clients and the server. So the load balancer is not used. Next slide, please. So to evaluate this, we took that very simple setup where you have a 100 megabit per second link between the client and the load balancer. The load balancer is a traditional Linux LVS. We didn't change anything. It's just like it's used in the wild. Then all the servers have a direct 1 gigabit per second link connected to the server. We run a lot of clients, HTTP clients, that are downloading or uploading files between the client and the server. So what you would expect showing that is that the clients download that roughly 1 gigabit per second in Mptcp and roughly 100 megabits per second in TCP. Next slide, please. So the result, there were a lot of figures. So I will not be able to prove anything here because I need a lot of figures to prove what I'm saying. So you have two solutions. You believe me or you read the paper after. But if I have to present all the figures, this discussion will be longer than the one on the proxy, and nobody wants that. So So what we see here is basically Mptcp is not affected by the loss. Here, yeah, clearly it's not ramping up fast, but it's because of the latency. We have a 200 milliseconds latency. If I showed you the figure without the latency, you could see that actually Mptcp is not affected by the loss. It could be if the ad address, and that's why this proposal was important, if the ad address is not reliable when you have loss, this will impact Mptcp a lot for bigger file size, because here we were downloading 4 gigabytes in total, split in 1 KB, 10 KB, 100 KB. So if when you have very huge file size, if the ad address is lost, the fast subflow will not be established. And then it costs a lot in terms of performance, because you will download a big file via the 100 megabit interface. So if the address is not reliable, I can show the plot here because I don't have time, but basically it affects Mptcp a lot, because here, instead of ramping up, it's just crashing, because each address lost means a big file that has to go through the 100 megabits per second link. So the bigger the file, the bigger the cost of losing the ad address. So with that kind of situation, you really want the ad address to be reliable. Next slide, please. So something else now, we also applied that to Anycast, because yeah, it works with load balancer, but it also works with Anycast. So in this simple schematic, if the clients, so those two servers are announcing an Anycast address, the same Anycast address. So before the red cross, if R1 wants to connect to the Anycast address, it will be routed directly to R2 and then to the server. If during the TCP connection, the links between R1 and R2 fail, then the client will be sent to the node that is connected to R4. Then what happened to the TCP connection? It's reset. And we don't want that, because if I was downloading a huge file and then cut in the middle of that and I receive a reset, I will have to start again probably. So I don't want that. So next slide, please. We made a setup to simulate that. On the router here, you have the Anycast address that is routed through the server. Each server does have the Anycast address and a public IP on the same interface. So it's just a routing configuration. We are not removing a link, but each server does have the Anycast address on the loopback and public prefix. So what do? We will send packets. The router will do some ECMP and basically just load balance the traffic among the 3 servers. So what happened next, please? So what happened? We simulated a reconfiguration in the network, like I showed 2 slides earlier, when the links go down. So we have 3 servers, and every 10 seconds, we remove a server from the CMP pool. So all the traffic will have to go to the 2 servers. What do we see on this graph? Is in blue, it's the total bandwidth. So when everything goes fine, we have roughly 3 gigabits, because each server is connected to via 1 gigabit link. So you have 3 gigabits, but when one server goes down, you are down to 2 gigabits, which is the sum of the 2 other links. So that's expected. So you see every 10 seconds, we have a drop of roughly 5 seconds, because that's what we do. And then we re-add it, and that's why it's ramping up again. In red, you see the resets that we have received, and that's the problem that I described earlier. Is when you are reconfigured to another server, you will get a reset. Here, you see that we have huge spike in resets when the server is removed from the ACMP pool, which is logical because that server cannot be reached, so you are hashed to another server. But we also see a spike in the resets when the server is set back again, because ACMP just recomputes all the hash, and then a fraction of the flow will be sent to the server. So you will get reset in that case too. Next slide, please. With Mptcp, that's what we expected. We have no drop in the bandwidth and no reset is sent. Why? Because even if the Anycast address subflow fails, the direct connection to the public IP address is not disconnected. It means that no client will be interrupted during a download. Sure enough, if the server stays down and the connection from the client is terminated by the client and then reestablished, then it will be hashed to another server. But with Mptcp, you basically allow your clients to finish what they are doing when you are reconfiguring the network. So when you reconfigure the Anycast network, you don't disconnect people. They will just have the time to finish their download, and then they will be hashed to another server. Yeah, it's okay. So in conclusion, we made some simple change to Mptcp, and I have to insist it's very simple, and that was the idea. To make it work with unmodified load balancer, we are improving the performance, the reliability, and we are solving the bottleneck problem we have with net configurations. And we also allow Mptcp to be deployed and used in any cast service, which is a new use case. I don't remember even seeing anything said about that. So all the results will be presented in a paper that will be presented in October in ICNP in Toronto. And that's it for me. Yeah, Alan.
I just wanted to clarify, this is using vanilla 6824 bits as it stands now. This wasn't any further modification.
Yeah, no, there is no modifications done here.
Thanks.
Alan Ford. Great, thank you.
Thanks, Sammy. Let's just see where we're at. Excellent. Olivier. Oh, it's not Olivier. Oh. How is the blue sheet doing? Where's it got to? The blue sheet? Where is the blue sheet? Has everybody on this side signed the blue sheet? One or two haven't. And nobody on this side signed it. Can we keep it moving? Yeah, sorry. Thank you. Quentin.
So hello everyone, I'm Quentin, and I will do a short presentation about the hackathon, what we have done, and to trigger some discussion about the RFC 6824 bits. So next slide, please. Okay, so we did a few stuff related to multipass CP, some usage and so on. Related to the socket API usage, about documenting multipass CP, and other stuff that are related to new feature added in the BIS version of the RFC. So next slide. So this presentation will mainly focus on these three propositions in the BIS. And so next slide. So first, the multipass experimental option. So basically that this allows us to exchange opaque data between them via an option that can contain basically anything. It was partly, during the hackathon, we partially implemented it. So we done the transmission and the parsing at the option reception. And the main thing that we need some clarification about this option is what about the S bit, so the synchronizing bit. So basically what it does, it says that when you set the synchronizing bit, you require that, or at least you expect some response from the remote host. And the question is about, is that to be reliable? What about if the packet that contains an option with an S bit is lost? Do we have to ensure that it is sent or not, basically? Yeah, it's an open question, actually. So next slide.
So we may come back to that when people have had
Yeah,
a chance to ponder it.
Probably. So about the multipass TCP reset option. So basically this allows us to explain why our subflow was reset on an Mptcp connection. So it is implemented in Linux, so it's okay. And we raise additional discussion about this. So the first one is about, we have the T bit that said that is the error transient or not, to know if it is worth trying to reestablish a subflow. Does that is to be taken into account if the code is different from the multipass unspecified reason for a reset. So for instance, if you have, let's say, a multipass specific error, does it have to be taken into account by the receiver? Also, another thing is that the option today is only sent when we try, when we decide to send the reset, but we don't keep state about why we reset the subflows because of memory reasons and resource reasons. So next slide, please. And about the reason code that were defined in the RFC, we found some cases where we can define additional code. So the first one is, what about if you try to do a MP join with a token, but the token does not exist anymore on the server you try to establish a new subflow? Does it work to have a new reason code or not? Don't know. Then what about if a subflow timeout for the remote host, and but the connection is still alive? So for instance, you sent a lot of data on one subflow, and then you decide to use a second subflow that was established much before, but it was removed because the server did not use the subflow. Does it has to have a special reason code for that? Also, if we decide to remove a subflow because we had a remove address, do we have to set a special code reason for resetting this subflow too? Yeah.
All right, I thought let's quickly tackle these, but any bigger discussion should probably be taken to the list. But the general point is that Mptcp reset option was to be analogous to an actual to go on a TCP reset on that connection to carry some additional semantics.
Mm-hmm.
So, for example, unknown Mptcp connection, there really is no point in sending that out. You don't want to differentiate that. You don't want to even go anywhere near the Mptcp rest of the implementation for that. Timeout. Again, the reason codes are all things that I'm trying to remember now. When we talked about the reason codes, the general logic was if it could either be useful for an administrator to analyze a problem or for an automatic resolution to the problem. For example, if it was a transient problem and it knew it was low on bandwidth due to that error, then later on it could try again, for example. But we don't necessarily need reason codes for everything. Certainly, we only have a limited number of bits to play with here as well. And the previous slide you had, should T be set for anything other than 00? Well, yeah, because it's got stuff like lack of resources or unacceptable performance. Those are exactly the kind of ones that would be transient that you'd want to look at later.
Okay.
But I think that whole list of questions is ideally suited for an email rather than a discussion.
Yeah. We can continue the discussion on mail. There is no problem. Yeah, and also we did not use yet the code about administratively prohibited creation of subflow and when you have too much outstanding data on a given subflow. But maybe we will find where to put this. But no. And next slide. And there is also the new multipass capable option that was made by Christophe. So basically, it allows to use connection keys that were defined at a higher level. So you don't need to send the keys in clear over the connection. And I think it works according to Christophe. So yeah. And that's it for me.
Is there any reaction to this slide now people have had another minute to think about it? Or does this need to go to the list?
Alan Ford again. Yes, it needs to go to the list, but I think it should be a fairly straightforward fix to talk about retransmitting here. I just don't think we actually covered that too much, but it should be an easy fix.
Julius Krobachek, for the peanut gallery, the people who have come here out of sheer interest, what's the application of this thing?
What's the application? Does somebody want to take that question?
experiments. Local experiments is the answer.
So if you want, for instance, to exchange additional data about, let's say, a subflow, or to do local experiments for to deploy new stuff, it's basically the option it's intended for. So.
Thanks, Quentin. So I skipped over, which I shouldn't have done, just an open call if there are any other updates about implementation news that anybody wants to share. I know in the past we've had several other operating systems that have talked about or have got some of the way through or have got a lot of the way through implementing multipath TCP. So we just traditionally have a moment for anybody who has any other implementation updates and they want to share anything with us, for them to do so if they want to. Okay, so we will move on to the protocol BIS spot with Alan.
This is super fast. There is one slide, apart from the title slide, which obviously we're trying to get to. Thank you, Phil. This is really weird, this screen down here. This is all odd. I feel I'm looking at my feet. Right, 3 changes in 08 as based on feedback, implementation feedback, which is, of course, the driving motivator here. Christoph's implementations pointed out quite significantly there were some issues around clarifying that when you send data on the 4th ACK, so with the MP-capable option being used to provide a data sequence mapping, you could end up with a situation where one end sends a data sequence signal, the other end sends an MP-capable, and they cross. And one end was expecting one and one end was expecting the other. So it's just to clarify that these mappings are identical and should be treated as identical when they turn up into packets. Similarly, also the retransmit logic for an MP-capable with a data mapping in it. By just saying they're equivalent means that the problem kind of goes away. I said thanks Olivier on point 2, but I actually realized it was actually Quentin rather than Olivier. My apologies, Quentin. But thank you for clarifying that the TCP reset in the fast close situation also put in. And finally, the update to SHA-256 has gone in, although I looked again and realized my search and replace wasn't quite as comprehensive as it should have been, and there's a couple of SHA-1s left, but I'll get rid of those. That's it on the update. And I don't think we have anything outstanding at the moment. There's no one's proposals that have any protocol modifications lined up. There's nothing I'm aware of that has anything lined up we need to worry about either. So, yeah.
So I guess there's a question if which we probably should revisit on Friday, if anybody has anything that they are about to suggest that implies an addition to the protocol BIS. Because if they have, I guess we should think about that before we declare victory and close it. And the other question is about implementation. So have we got an implementation of all the new bits that have been added to the BIS now, or not quite?
My understanding, although Christoph might shout and clarify, my understanding is this recent hacky work on iOS and Linux is now pretty much got all the BIS changes up to date now. Not quite. Okay.
Can you come to the mic? Can you battle away through?
Or one of you can clarify.
At least Linux, like we during the hackathon, we implemented with Olivier and the rest of the team. We implemented all the BIS pieces, but iOS no.
Okay, sorry, right, yeah. So it's not that we haven't got an interoperable implementation of all, but we have one implementation of everything.
So your Linux implementation that's now publicly available has all the BIS items in, or the bit is going to be released soon, basically.
Yeah, the code
You have
still
an
needs to be
internal
released.
version.
Like none of the code that was worked on during the hackathon
Has been released.
has
yeah.
been released. No, yeah, but I guess this will happen.
But yeah, okay. So pending a kind of just pushing it out, then it is now everything in the BIS has been implemented. So I guess that, Mia, is that enough, one implementation, to push it in standards track and send it? I don't know what the current view is on these things.
I think that's mostly the judgment of the working group, because there's no
Right.
common
okay.
rule, because all the implementation, all the protocols are so different.
Okay, right.
It should be justified in the Shepard write-up.
Right, okay. So we'll have to discuss that. I mean, we've got two implementations of almost most of the protocol, and then there's these new bits in the BIS would have one implementation. So we'll have to talk about whether that's adequate. And yeah, maybe we should talk a bit more about timings on Friday. Is the 256 SHA 256 implementation, is that in the BIS or not as yet? Not yet. Okay. For people out there, that was Christoph saying it's not yet in it. Okay, so we should try and work out a plan of how we're going to push this forward in the next month or so. I think we need to get a security area review to make sure that they're happy. We will think about if there's any other area reviews that should be done ahead of pushing it out, because they'll kind of get done in the formal process when it goes into the ISG and things, but we probably should start that early. Okay. Any other comments or thoughts on the protocol BIS? Perfect. Okay. So we're now moving on to our proxy mini session with excuse me, with two new drafts, one from Olivier and one from Vlad. So we got a good deal of time for discussion about both of them. What we got about 65 minutes or so, just over an hour. So we should be able to get a good discussion about them both. Now, how are the blue sheets doing? I haven't seen it come done. Oh, it has. Who has not signed the blue sheet yet? It's the odd person. Right, Olivier. Do you want to use your own? Yeah.
Okay, so let's go back to the proxy work, and let's first come back to the motivation. So if you remember, if you were in Mptcp since the beginning, you know that we've had a lot of troubles with middle boxes, and we had to fight a lot with the middle box, and we managed to have something which works over the global internet. And now the next question is,
can we design a middle box that would benefit to MPTCP? So can we get something more thanks to the utilization of a middle box? And this is part of the charter. And at the bottom, you see the current charter of Mptcp working group. And during the last year, there have been several proposals that have been discussed. So there is a draft plain mode, which has been mentioned earlier. There is a draft transparent mode. There is SOX 5. There will be SOX 6 that will be presented by Vlad later on. So there is a family of solutions that try to address the problem. And in this talk and in the draft, we have tried to restart from scratch based on all the discussions that have been made on the mailing list to have a design which is cleaner and we hope easier to understand, easier to implement, and which provides all the use cases that we would like to have with MPTC proxies. And to distinguish that with what you might think about proxies, we have decided to use another name, which might change later on, but the name that we use is a converter. And our motivation is that there are now far more MPTCP-enabled clients than MPTCP servers. And for all those clients, it's very beneficial to be able to use MPTCP on a part of the network when reaching a server which does not support MPTCP. So there is a clear use case, and there are other use cases for those kind of converters that have been discussed earlier, but I will focus on this use case now because that's the simpler to understand, and if you want to understand the basics of the protocol and the basics of the solution, it's better to start with the simple use case. So let me first try to summarize what have been the discussions in February, March, and April on the mailing list. So first point is that if we use a converter, one key point is that we do not want the converter to significantly increase the connection establishment delay. So we don't want to lose 100 milliseconds because we are going through a converter. So that's the motivation for having a solution that requires 0 RTT in contrast with SOX 5, for example. Second, we do not require the utilization of the converter for all the traffic. So it should be possible for the client to use a converter for some specific connections, not all the connections. And in particular, it should be possible for the client to decide to bypass a specific converter if it knows that the final destination supports MPTCP. Because if you have MPTCP end-to-end, then there is no need to go through a specific converter to give you MPTCP for one half of the network, while you could have MPTCP for the end-to-end path. There have been lots of discussions on whether we would use TCP options or data in the payload. And one of the questions that was raised by Joe Touch and Julius was that if you place data in the SYN, you have to use TFO, and TFO is a standard solution. And we need to be able to use TFO not only for the connection between the client and the converter, but also for the end-to-end connection between the client and the server, as we see that there is more and more support for TFO. And finally, the design should be extensible and future-proof, and we should avoid defining new TCP options because you know that putting new TCP options in a SYN is a mess when you already have the MP capable, the timestamp, and all the other options that are already present there. So what is the cleaner design that we came up with? So we have an application level protocol that uses a specific port. This makes it easy to deploy the solution similar to SOX. All the commands that are sent by the clients and the response that are sent by the converter are encoded as TLV messages, and using TLV messages provides extensibility. We leverage TFO so that we can put the commands directly inside the SYN, which is sent by the client, like SOX v6 that Vlad will present later on. So the commands and the response are sent inside the SYN. And we have a solution to allow the clients to learn what are the TCP options that are supported by the final servers. And this is required if we want to be able to bypass a converter, because we will bypass a converter if we know that the final server supports MPTCP in the case of MPTCP. So let's start with an example. So there are 3 hosts in this example. You have the client at the bottom, the server, and the converter, which could be anywhere. If you want to create a connection towards the server via the converter, what do? You first send the SYN from the client to the converter by using the converter IP address and the port number of the converter. Inside the SYN that you send, you place a TFO option with the cookie of the converter. Let's call this cookie T. and inside the payload of the scene, and all the information that I will show in blue will be TCP options, and the information that I show in red in the packets will be payload information, which is encoded as a TLV messages. So in the payload, I have a TLV message that says, please connect me to the server S on port P. Nothing really strange. So when the client receives this SYN message, what does it do? It will create immediately a SYN towards the server. The server will receive a normal SYN, and it can reply with a SYN with a SYNAC that goes back to the converter. And the converter will return the SYNAC to the client to confirm the establishment. At that point, we have two TCP connections. There is one connection from the client to the converter, and one connection from the converter to the final server. And these two connections are glued together in the converter by the application running on the converter. So all the data that comes from the client will go to this connection, and all the data that comes from the server will go to the connection to the client. Nothing really difficult. Okay? So let's look at that in more details with two examples with different TCP connections. So our motivation is Mptcp. So let's look at what happens when you try to open an Mptcp connection through the converter. So to open an Mptcp connection, I have to put the MP-capable option in the SYN. So I put the MP-capable option in the SYN, and in the payload, I indicate that I want to connect to the specified server on the specified port. The converter will send a SYN which contains the MP-capable option to the final server. And let's assume that the server supports Mptcp and uses RFC 6824 bis, which means that it provides its key in the MP-capable option while there was no key in the MP-capable option of the SYN. So you have the key of the server, which is returned as a TCP option. The information arrives on the converter. And what the converter does is that it accepts the establishment of the connection. And once you have accepted the establishment of the connection, you need to inform the client that the connection can be established, and you need to let the client know that the server supports Mptcp. And to do that, what we do simply is that we copy the content of the extended header. So all the TCP options that were in the SYN plus ACK, we put them inside the TLV message, which is part of the payload on the SYN plus ACK, which is returned to the client. And then the client, when it receives the SYN plus ACK, which contains this TLV information, it will know by parsing the TCP extended header that this connection to the server will be using Mptcp from the client to the server, so that the next connection that the client will want to open to the server, it will know that this server supports Mptcp, and so there is no need to go through the converter to reach this server. TFO. We want to use TFO here. That's easy. But we also want to be able to use TFO from here to there. Let's look at what happens if we want to use TFO through the converter. So again, we assume that we already have a cookie from the converter because we have had many connections through the converter. And if I want to do TFO with a server, you remember that in TFO, we do that in two steps. First, I send a TFO option which is empty to the server. The server replies with a cookie, and then I can use a cookie to send data in the next TCP connection. So how do we do that when we have a converter? I will send a SYN which contains the TFO cookie of the converter inside the TCP option. And in the TLV message of the SYN, I have the connect command. And I have additional information which contains TFO, an empty TFO option. So the converter will recognize that, and it will send a SYN with an empty TFO option to the final destination. So the final destination receives a SYN with an empty TFO option. What does it do when it receives a SYN with an empty TFO option? It returns the cookie that corresponds to this TCP connection. So the cookie, let's call this SC. The cookie SC is returned back to the converter. And the converter does the same as with the MP-capable option. It simply copies the TFO option and puts it back inside the payload of the SYN plus ACK, which is returned to the client. And the client can extract the server cookie and use it for the next connection that it will create for the same server. So let's look at the next connection. So this is the second connection. On the state of the client, we have the server cookie, which is known. So when we send the scene to the converter, this is a scene that contains data because we are using TFO. And before the data, we have the connect command, and we have the TCP option, which contains TFO and the server cookie that we have received in the previous connection. The converter will copy this information in the scene that it sends to the server and will copy the data. The server sees the server cookie that it has sent for this specific client. It recognizes it and it accepts the data. And then it replies with the SYN plus ACK, and the SYN plus ACK is returned to the client and the connection is established. So we can support both Mptcp, TFO, and other stuff with that.
Yoshifumi has a question on the Java room. He asks, in the Mptcp case, when you convert to Mptcp, who decides to actually do this? Is it the client or the converter?
Who decides to do what?
So the question is, when the converter changes TCP into Mptcp, who's deciding this, the client or the converter? That's the question.
When the client changes Mptcp?
No, the converter.
When the converter changes Mptcp to?
No, TCP to Mptcp.
But this is Mptcp. So you have Mptcp and you try to establish Mptcp. So I'm not sure I understand the question.
Me neither. Maybe he says something later on. I'll let you know.
So of course, if the server does not support Mptcp, then you don't have MP capable back, and you learn that you have Mptcp here and regular TCP there.
Hi, Alan Ford. How do we, this may be coming up on another slide. How do we add another subflow to this?
Well,
if the client wanted to talk directly to the server at this point, since both ends can be...
So when you have that, you have two TCP connections, or two Mptcp connections in this example. You have one from the client to the converter, and one from the converter to the final server.
Yep.
So if the client adds the subflow will be added between the client and the converter. If the server adds a subflow, it will be added there.
So nothing would go direct from the client to the server?
So it's not a bypass where you can go direct from the client to the server. So this would add lots of complexity to do that for a single Mptcp connection. And I think it's easier to just test the first connection. And if you determine that the destination is MP capable, then you can open the next Mptcp connection towards this server.
Oh, I see.
In many use cases, you have a large number of connections anyway to the server. And if not, you can apply a kind of API-able solution, or you can also try to open in parallel two connections, one via the converter and one directly to the server, and you just take the one that does Mptcp and works correctly.
Okay, so the presence of all this red stuff tells you that the
red stuff here tells you that the server supports Mptcp.
Right, and of course that wasn't in your previous example.
And in the previous example, it wasn't there.
Okay, thanks.
Hi, Vladimir Oltano. So my question has something to do with TFO. Isn't it a bit dangerous to tell the client your TFO cookie? So the client gets to know the proxy's TFO cookie, and then it can do all kinds of nasty stuff with it.
Yeah, so the question is, why do you give the TFO cookie to the client and not keep it on the converter itself?
Yes.
It really depends on what's your type of deployment that you have on the converter. So if you think of a converter that has a single IP address, and this single IP address is shared by all the clients, then you don't want to reveal the cookie which is mapped to this IP address to all the clients, because they could be able to do traffic directly. But if you have a deployment where the converter has not a single IP address, but a pool of IP addresses, and you map client address on one address of the pool, for example, then it makes sense to send the cookie back to the client.
I see. Okay, thanks.
I see that there's the TFO cookie T inside the SYN sent to the converter. And so it kind of, I think in the draft it said like it recommends to proactively refresh the cookie. So my question is, how much do we rely on TFO for this SYN? Like, if for what another reason, even if it's not because of the cookie, we fall back, does it still work? I think so, but.
So so the question is, what happens if, for example, the converter changes its cookie, and so we have a wrong cookie on the client side? But that's the normal procedure of TFO that would apply there. So you would not hack the content of the data. So you would not hack the message there, and there would be a fallback, and you would restart, and you would have 2 FTT instead of 1 FTT in this case.
The leg to the server will be extended.
Yeah, and that's the normal TFO procedure. So one of the objective of the design was to have extensibility, and if you think about extensibility, there are 2 dimensions that needs to be considered. The first dimension is the extensibility of the application level protocol that includes the TLV messages, and we get that by using TLVs and version numbers. So we have a solution which is easily extensible, and you have to look at extensibility from the TCP viewpoint. What happens if TCP is extended, and if someone has another crazy ID than Mptcp? And we would like to use that through the converter. Well, this is feasible as well because we can detect what is the TCP options that are supported by the server. So we have flexibility and extensibility in the design of the protocol. So the client can decide to bypass the converter once it has detected that the server supports the options that he would like to use. So if at one point all clients are using Mptcp and all servers are using Mptcp, then all clients will detect that there is no need anymore of the bypass, and nobody will use the bypass anymore. So now let's go back to the criteria that Phil and Yoshi sent on the mailing list about how to compare different solutions for proxies. So the criteria, and I tried to summarize the email because I could not fit the content of the email in a slide. So the sentences were pretty long. So first comment was no changes to Mptcp. So there is no change required to the current spec. Proxy is simple to operate and deploy. Well, this is like stock, so we need an IP address and a port number. So you can place the converter anywhere in the network. So this is existing best current practices. Session can be initiated from either end. We believe this is feasible, but this is not part of the first draft because we want the draft to be simple. Setup type is minimized, so we provide that thanks to the utilization of TFO. Design minimizes the amount of overhead on data. Basically, the only overhead that we have is the TLV messages that we place inside the SYN and the SYN plus ACK. So the overhead is only for the SYN. We don't need any encapsulation scheme. And the solution works if end-to-end encryption is in use. The solution is compatible with end-to-end encryption. The only issue is that if you use different IP address on the client and on the converter, you would be in the same situation as with a NAT. And so if you have an encryption that relies on the validation of the IP addresses, then you will have issues. Other criteria that were mentioned for single-ended proxy scenarios. The proxy is unlikely to be on both default paths. So this is the case. The converter can be anywhere in the network. Clarify whether the proxy simply forwards. Well, the converter terminates TCP connection and maintains states for the 2 TCP connections from the client to the converter and from the converter to the server. Allows hosts to have traffic that doesn't get proxies. So this can be based on policies or automatic bypass once you have detected that the server supports the TCP option that you want to use. And host and proxy need to authenticate. We believe that it's possible to put authentication scheme in the protocol by using the TLV messages. But if we say the word authentication, then we'll have 20 people in the IETF saying that you would like to support our authentication scheme, and it will not be a draft, but 5 drafts. And so I want to keep the solution simple, but we can add authentication schemes inside the draft as well. So to conclude, this is a new design which takes into account all the commands that have been raised on the list. That's an application level protocol, so we will have to reserve a service name and port from the INA. It provides 0 FTT using TFO, which was the key issue, and the client can bypass the converter if the server supports the option. And our request to the working group would be adoption of this document for charter item. And with that, I've covered all the basics. The details are in the draft.
Julius Krobacek. So I'll make some more substantial comments perhaps after the SOC 6 talk. Here I have just two minor comments. One is about extensibility. I haven't found in the draft where you say what to do when you see an unknown TLV. The intent is pretty clear, but you don't actually say it.
When you see an unknown TLV,
yes,
or there is an error TLV in the draft,
yes.
and so
you give the error, but you never say what to do.
Never say what to do.
You never tell the implementer whether that he should return the error and drop the connection, which I assume is the intent. Okay, this needs to be said. And the other thing, so again, that's something, the intent is perfectly clear. So you say that it's a normal user space proxy. Now you are doing some rather exciting stuff with TCP in here. Okay, for very good reasons. I understand very well why you're doing that, but you're returning the unchanged SYN header, SYN-ACK header, and you are actually replying by a SYN-ACK only after you've received the SYN-ACK from the other side.
Yeah, and the reason why we are replying with the SYN-ACK only when we have received the SYN-ACK is that we want to be able to test whether the connection to the server works correctly, because we know that there are many API-ball solutions where you try to open multiple TCP connections in parallel to a given server.
Mm-hmm.
And it's important that you are not in a situation where some of the connections always succeed, even if the server is not there, because this would produce new types of failure scenarios that would be difficult to detect by the applications.
Mm-hmm. So that's for very, very good reasons.
So it's clear that there are some small changes to be done to the interactions between the application and the TCP stack.
Yeah.
This is not something that a student who is doing networking 101 will be able to implement in one afternoon.
Nor even 301.
Yeah.
So there's more on Jabber. I have to admit I don't get the question, so I just read it out loud. In the scenario of a middle box between an end device, with only plain TCP support and a middle box talking to a server in the platform in Mptcp, is the client the middle box? So there's more. The middle box would implement a TCP proxy for the end device and send the traffic in Mptcp to the converter, or possibly directly to the destination server if it is detected to support Mptcp.
I suggest to put that to the list.
Yeah.
Mia Kühlewind, is this working here? As you say correctly, this is kind of an application layer protocol, and it's also not, it can be used for other things than just Mptcp. So I assume this is not the right group. Sorry to say that.
So the discussion on the mailing list was that it was important to have a solution which is extensible.
Yep.
So we came up with a solution which is extensible.
No, I mean, this was not a comment about this is the right or wrong solution or whatever. I just think this is the wrong group to work on this solution.
You're speaking as an individual or as an...
Right now as an individual, but I can change it anytime.
No, but
I think, yeah, just one clarification to this one. I think that's, yeah, it depends what ambition do we have as a working group. If we want the solution to be specific to the Mptcp, the document will talk only about how we will handle the Mptcp connections, and we don't talk about the other usage outside Mptcp. So it's just a matter of, I would say, scoping of the document. So if that's what we want, we can say clearly in the specification that it's only for handling the MP capable, and the handling of other TCP option is out of scope of this document, and we are done. For me, it's just a matter of scoping of the specification. Yeah.
So, I mean, like, you cannot say you can use it for other things, but we don't look at it, so it's scope. And further, if it's an application layer protocol, which is, I think, the correct term, it's not Mptcp.
We have to remind ourselves why we ended with the application layer proxy. This is one of the main comments that we received in the mailing, that people say that if you wanted a proxy, just reserve a port number. And we are hearing what the working group wants, And that's why we are asking to raise the port. If now you say that's no, this is the direction,
So-
we go back to what we have earlier. That's
no, no.
So this is the right direction, but it's not the right working group.
So I'll make.
Yeah, and like actually, additional question. Say this also say. Then I thought about which one is the right working group. Right, don't have a good answer yet. But to some extent, it sounds a little bit like ICE as well. So maybe this is something to look at. If you can use existing protocols for this use case.
But then my question will be, what do you think will fit in the last charter item, which is the working group will explore whether an MPTCP OA middle box would be useful, or
So
at least one I know is MPTCP enabled. So if you look at the charter on the first slide,
Yes.
I think we are answering the charter.
So this charter doesn't.
So the charters defines what
yes.
the working group is expected to do.
Yes, but it doesn't mean that this has to result in an MPTCP document or in any kind of outcome. It will explore the options, and probably what's really in scope would be maybe an informal document that is describing how to use options that may or may not be developed in other groups.
So I think we should talk about it off in a sort of smaller gathering, because it's quite tedious for most people which IETF working group things are done in. But I mean, I'm happy for us, it's relevant to multipath TCP, to give it some time is great. If it has to be talked about in other groups, that's fantastic. Yeah.
Ford, it may surprise you that given how much I've been banging on about application layer protocols for a while here, this one strikes me as being very MPTCP specific, because it's all about shifting the options around, the MPTCP specific options. You haven't looked at how to use it for other options, and plus what's more, that's out of scope. It's in scope as an MPTCP solution, and as you say, it matches a charter, so actually I think it's quite a good match for this working group.
So what I propose at this point is that you actually go and contact other working groups and maybe even present this in like area meetings and stuff and get some feedback about it, and then we can see if there's any other working group that thinks it's in their scope and should be done in their working group, and if not, we can do it here.
And how many working groups do you want us to look around until we have a decision?
I was concretely thinking about probably TCP area and int area. Or actually, think about it.
Are there any?
So
I don't mind us talking about this more, but are there any kind of technical questions about what Liv is presented?
So
or
technical issues are.
I think
we have to separate in two parts.
Discussion about that rather than.
So technical issues, and then in which working group this could fit, because that's
Yes.
another issue.
No, I was kind of waiting to see if there are more people coming to the mic, and there weren't. So, but like we can also talk. But I have a little bit of a technical question, which was related to Alan. You did say this can be used for other TCP options, and when I look at it, I think it would be super easy to use it for other TCP options. It would like be straight, right? Like there's actually no change required. So I think this is actually not MPTCP specific. It's TCP specific, yes.
Yeah, but MPTCP is an extension to TCP. So, of course, any solution that we do with MPTCP will work for regular TCP as well. So we are.
Yeah, but I mean, we also have a TCP maintenance working group.
Of course. But they never had this issue. So they have produced Windows scale, they have produced timestamp, they have produced lots of draft and lots of solution, and they never had this issue because there was no use case where you have two access networks and there is a strong benefit of having MPTCP on the part of the network. They haven't seen that use case. So this use case comes from MPTCP and from the utilization of MPTCP.
I think that you have a proxy that implements a new option while like one of the endpoint doesn't implement the option is a very general use case for all kind of TCP extensions. The benefit here is larger than for other options, yes, but they have this use case.
Yeah, but they don't have documents on explaining how to do this use case as far as I know.
Because nobody proposed it, so you might propose it there.
Julius Krabacek, I would just want to add one element to the discussion. This is actually a quite manageable document. I've actually read it, all of it. And it's written with an eye to something that we sometimes neglect, that is implementability. Okay, there are a few things. So for example, there is one thing: you cannot take a domain name, which makes it, and since you are doing strange things with TCP, you might want to implement it in a specific environment. So the fact that there are no domain names makes it much more implementable. And I cannot help but wonder whether if this document goes through a number of other working groups, it will still be a manageable and implementable protocol.
I'm not sure, but the reason why there is no domain name in the connect message, in contrast with SOX, for example, is that we want to provide zero RTT. So we don't want to be in a situation where when the client sends a connect request to the converter has to do a DNS lookup before sending the SID. And that's a feature and not a bug.
And the side effect is that it becomes doable in kernel space, which
Yes.
is a welcome side effect.
Yeah, that's a side effect. Vlad?
Any more comments? Me.
So as an AD, I think I would like to advise you to announce it on the TCP area and TCPM mailing list and get some feedback there.
Okay, do you want us to try to present that this
No,
week?
just put it on the mailing list, you will get feedback.
Okay.
Just to add to Julius's comment, it is nice and readable, this draft. It's good, so thank you and congratulations to the people who wrote it. It's got nice protocol modeling and stuff, which is how people are advised to write this sort of document. So it's, you know, don't be, I'm basically I'm trying to encourage everybody here to go away and read it. You will be able to get through it, I think, and it would be great to have comments from people on, I was going to say on our mailing list, but on any mailing list you fancy. But start on this one, that would be great.
I also just want to say, as an individual contributor, I like the proposal.
Yeah, and thank you to the authors for really listening to the feedback that they've been on. Yeah, thank you to the contributors for really listening to the feedback that they've been on the previous documents and discussion we had last time, and the follow-on discussion to that, because it's really come over that you've tried to react to that. We've heard from at least one person, which is Julius, who had some issues with some of the previous approaches. And maybe it's worth trying specifically to get comments from some of the other people who had comments to see if they can live with the approach that's proposed. Because to ask your question about the that you want adoption, I think, well, firstly, we need to give people more of a chance to read it and get some comments on the mailing list, supportive or with suggestions. You know, and secondly, in order to have the consensus, it can be a working group item here or somewhere else in another working group. We've got to make sure that it's a solution that everyone can live with. I mean, that's kind of the definition, isn't it? So we've got to make sure that happens, or that people can come to the decision that that's you know, not a criteria. Any more comments? We'll probably on Friday have a little bit of spare time. Looking at the agenda, we've got an hour, and we've probably not got an hour's worth of stuff. So if people have the chance to read it before Friday, either this and the SOX draft, we probably can have a little 10 minutes or so slot where people can come up with the questions that they've thought of in the time that they've got during the busy week to read the draft and think about it a bit more. Thank you very much. So next up is Vlad, I think. Do you want to use my laptop?
Sure.
Yeah. one are we on? Which one? Are you one of those?
I don't think so.
I thought I'd open them all.
Should be called SOX 6.
It should be called SOX. Is there SOX one there? No, I thought I'd saved them all. I haven't.
There we go. Cool. Okay, so I'm Vlad, and I'm going to talk about SOX protocol version 6. So next slide, please. So SOX 5 is 20 years old, and it really needed a facelift. The main problem with it is that it makes liberal use of round trips. So we've got one round trip for negotiating the method of authentication, then another round trip or maybe more for authentication, and then the client can finally request the establishment of a connection. Now, not only is it very chatty, but in the meantime, there have been people have been developing zero-RTT authentication methods. So if the two entities had already communicated, they can authenticate in just in only one message in further connection attempts. So now we have this hot new use case where mobile users might want to use both their cellular interface and their Wi-Fi to basically get more bandwidth. Now the problem is that there's little to no Mptcp usage on the server side, so we need a proxy for that. And since these mobile networks have high latency, we really have to trim down on the RTT usage. So next slide, please. So in SOX version 6, we've done exactly that. So the client is very optimistic, and it attempts to send as much information up front as possible without waiting for the authentication step to conclude, if any authentication is required at all. So it advertises its supported authentication methods. It asks the proxy to establish a connection on its behalf, and also supplies some application data if it has application data available. And it also specifies whether the proxy should use TFO or not. And finally, it's also extensible. So we've added TCP-like options in order to do all kinds of cool stuff, like maybe ask the proxy to use a certain Mptcp packet scheduler or whatnot. These still remain to be discussed and standardized. And via these options that I've mentioned, zero-RTT authentication methods, zero-RTT authentication can be done via these options. So next slide. So let's take a look at how SOX 6 looks when compared to SOX 5. So in SOX 5, you can see that the client first advertises its authentication methods, and then the authentication proceeds, and then it sends a request, gets a reply, and then it can send data. So we've moved those 3 bits, the blue bit, the green bit, and the red bit. We've moved them, we've packaged them into one single message, which is the request, which the client sends at the very beginning of the connection. Then the server sends an authentication reply, which informs the client whether authentication has succeeded or whether further authentication is needed. Since this is the first connection, further authentication may probably be needed. After the authentication step has concluded, the proxy attempts to create a connection to the server and then sends an operation reply to the client telling it whether it had succeeded or not. So next slide, please. In subsequent connection attempts, the client can do zero-RTT authentication, in which case the server can attempt to initiate the connection as soon as it sees the request. So it sends an authentication reply and then an operation reply after after the connection has been established. So next slide, please. So let's take a closer look at the request. So it's basically a mishmash of the method advertisement message and the request, along with some data. So please note that the client can include in some initial data as part of the request, while still asking the proxy not to use TFO. The options are in TLB format, and they can aside from authentication, zero RTT authentication data, they can include all kinds of other stuff that has yet to be standardized. So next slide, please. The authentication reply basically tells the client whether further authentication is needed or not, and also tells the client which, in case further authentication is needed, which method for authentication must proceed. In case authentication succeeded, it informs the client via which method the client got authenticated. So for example, if a client connects to the proxy via its home Wi-Fi, the server probably expects some kind of authentication. But then if it connects to the proxy via its cellular network, the proxy knows that the client is that the client is actually a paying customer, and basically tells the client, hey, we authenticated you via the no authentication required method, so that the client gets to learn that it shouldn't attempt to do any kind of authentication when using its cellular network. So next slide, please. Finally, as soon as the proxy receives, so after the proxy attempts to connect to the remote server, it sends an operation reply, basically telling the client that it either had succeeded, or if it hasn't succeeded, it informs the client why it hasn't succeeded. So maybe the remote server has reset the connection, or maybe the connection timed out, or maybe the server is unreachable, or some other reason. Now, there's one field of particular interest here. It's called the initial data offset. So if you recall, the request includes some initial data. Now, if further authentication is required, the server has to buffer that initial data. This initial field, the initial data offset, basically gives the server a carte blanche as to how much of that initial data it buffers. So it can choose not to buffer any of the initial data while waiting for the client to authenticate. Otherwise, it is largely useless. So next slide, please. So let's see how SOX v6 fares in action. In case we don't have TFO on any leg, the client basically initiates a three-way handshake, and after one client to proxy RTT sends a request along with the initial data. The proxy also initiates a three-way handshake to the server and sends the data as soon as it receives the CNAC. In this case, it takes two end-to-end RTTs for a data response, same as with vanilla TCP. So there's no overhead in terms of delay. Next slide, please. Now, in case we have TFO on the proxy server leg, things get interesting. So the client gets to send it. So the client sends a SYN that also contains the request and some data that the proxy can send to the server. The proxy starts initiating the connection to the server as soon as it receives this SYN from the client. And as such, we shave off one client to proxy RTT. In other words, if the proxy is on path, we actually have negative overhead. This is highly advantageous for mobile networks where we have high delay at layer 2. So next slide, please. And finally, if we have TFO on all legs, the the SYN that contains the request basically gets translated into a SYN that contains the initial data and is headed for the server, and the server can replies immediately, and we get a data response in one RTT. Same as with TFO without any proxy in the middle. Next slide, please. So, can we use multiple proxies? Yes. One solution would be to run socks over socks. So basically the client makes a request that contains another request in its initial data, and the initial data of the second request is the actual data that has to make it to the server. Socks can be stacked over socks multiple times, and no matter how many times we stack it, the RTT overhead is the same. So we get the data response in two RTTs if there isn't any TFO available, or in one RTT with TFO on all paths, on all legs of the path, regardless of how many servers we stack, regardless of how many times we stack socks over socks over socks. So no matter how many proxies we have on path, we've got the same overhead. Alternatively, we could just configure the first proxy to go via the second proxy. The second proxy doesn't necessarily have to be a SOC6 proxy. We can use any other proxying technology. So next slide, please. So we do have an early prototype. So we have modified shadow socks. In case some of you might be familiar with that proxy. It uses its own protocol. We've modified it so that it speaks SOC6, and we've also created a library that you can use to create SOCS messages and write your own apps that use SOC6. By the way, this is an early prototype, and there are some differences between this prototype and the draft. So finally, I'd like to say some words about how this compares to the other solutions. So they are similar in that when you strip the initial exchange between the client and the proxy, you end up with the plain data stream. So it's, however, we use an entirely different starting point. So this is purely a layer 5 protocol. We do not use Synapse to signal that the remote server has accepted the connection or not. We actually use some TCP data for that. TFO or SYN data is not required, but it's required if you want zero RTT overhead. But if some middle box happens to strip TFO, then SOCS still works. And finally, if a middle box doesn't kill TCP, it surely can't kill SOCS. And with that, I'd like to thank you.
Comments, questions?
So first, thank you, Julius Krobacek. First, thank you, because when in the late 90s, early 2000s, we were upgrading our client software to use SOCS 5 instead of SOCS 4a, we realized there was one thing that was shocking, was that upgrading to SOCS 5 added one RTT to the unauthenticated case with no benefit whatsoever.
Yes.
So now we've recovered this RTT. So
well, you're welcome.
It took 20 years, but well. The comment I wanted to make is that I think it's important to stress how much Olivier's draft and your draft live in different spaces. And I think there is space for both. So this thing is something I would estimate that it would take 20 minutes to upgrade an existing SOCS 5 proxy to use SOCS 6 without authentication and without zero RTT. The simple thing would be very simple. I can imagine putting that in software that is not doing proxying just as a way of connecting to the software. I couldn't imagine using Olivier's technology for doing the same. It also has domain name, so it fits the needs of SOCS 5. So I think this has reason to exist even if Olivier's draft exists. The two are not at all mutually exclusive. And the other comment is, suppose that I'm writing a client for SOCS 6 Now, my client will probably want to speak SOX 5, want to speak SOX 6, and will want to be able to speak to protocol converters. It doesn't care which it's speaking to. It just wants to establish, it wants the weaker guarantees that SOX gives with respect to a transport protocol converter. So it doesn't care which it speaks to. But the packet format between the protocol converter and the SOX protocol are very different. So on the client side, I have to make two completely different implementations. Now, I'm not saying it's a good idea. I don't know if it's a good idea. Generalizing often yields completely unmanageable protocols. But I wonder whether it would be possible to consider having the same packet format for both techniques, and making it possible for a client, to connect somewhere and discover whether it's speaking to a protocol converter or a SOX 6 proxy.
Well, I mean,
I don't need an answer now. I'm just encouraging you to think about it.
Well, the thing is, it all has to do with the message format. So the very first byte of the data stream has to be 4, 5, or 6 in our case. So Olivier's solution should begin with 7 or 107 or some other number. But other than that, it's.
No, I'm thinking of a single client that connects to a proxy. Mm-hmm. It doesn't. Oh, you mean in the server to client direction? Yeah, sure.
Yes. So it basically should go like this. Hi, I'm a client. I wish to speak SOX version X. And then the server says, but I speak version Y.
So my question would be rather, shouldn't SOX 6 support both protocols in a single unified protocol?
Well, yes. I mean, if a client opens up a connection and says, I speak SOX 5, then the server should speak SOX 5 to it. So if you could turn back to the slide, it has the request on it. Yes. So the first byte is actually the major version number, same as in SOX 4 and SOX 5. So if a SOX 6 server gets a request that starts with a 5, just as in SOX 5, then it can start speaking SOX 5 to the client.
Yes, that's clear.
Mm-hmm.
That's clear.
I'm not sure how we can integrate that with Olivier's proposal.
In the converter message, we start with a fixed header that starts with a version number. And so if we say, for example, that version number below some value are reserved for SOX and higher value are reserved for converter, then
yeah, I guess that
we just need to make sure that we don't use the value 0 to 4 that you use. But I don't remember whether it's in binary or it's in ASCII code or whatever, but that this is feasible.
Yes, it's in binary format.
And I have a last editorial comment. The reason why you're allowed to truncate the data, the initial data, was not clear to me after reading the draft. It became clear after you gave your talk. So perhaps there is some discussion missing in the draft on this subject.
Yes, I will amend the draft.
Ben Schwartz. Okay, a few points. I don't know if anybody in here was in dprive this morning, but the proposal in dprive to recognize that two protocols happen to be demuxable on the basis of the first few bytes was extremely controversial because it tightly constrains future development of those protocols. Now, once there's a use base that relies on them being demuxable, they can no longer evolve to modify those bytes independently. They have to be considered as a single protocol. So that's a point that sounds very scary to me. I wouldn't want to do that lightly. The second thing I wanted to point out is that SOX 5 is an incredibly widely deployed protocol. in essentially every web browser in the world, and also quite a number of other places. I think your proposal is an improvement, and that's good. But agreeing on a new major version number of SOCKS seems almost as big as agreeing on a new major version number of HTTP, and again, is not something that I think we should just do within the Mptcp working group.
No, I actually plan on I actually plan to work on this in the int area.
Okay.
But this is of interest to the Mptcp working group.
Good. Yeah, in a major version number for SOCKS, I can think of a lot of other things that I would like to improve about SOCKS. So I hope that we don't just move ahead with an incremental change when there's a lot more things that we need that need work. And in particular, I want to point out that this protocol's major improvement is a reduction in round trips.
Yes.
That SOCKS proxies in general are used primarily in two cases. They're used on localhost,
Tor and stuff like that,
to a very large extent, and to also the remainder is largely on a LAN with extremely low latencies. So that latency savings is useful, but it's only really useful if the SOCKS server is at a large distance from you. And if the SOCKS server is at a large distance from you, then you do not have a trusted network anymore, which in my view means that encryption using TLS or an equivalent protocol should be mandatory.
Well, the use case that I mentioned on the very first slide was that mobile user, so 4G, 3G, and LTE have high delay. So if you deploy a SOCKS server one hop away, you're still going to get a high RTT.
In that case, you're over a wireless network with mysterious security properties. I would feel a lot more comfortable again if we specified end-to-end and client-to-proxy encryption.
I guess nothing stops you from running SOCKS 6 over TLS.
Yes, I agree that nothing appears to stop you, but I would point out that perhaps due to the lack of any recommendation in this to actually do so, none of the SOCKS 5 clients today perform any kind of encryption between the client and the proxy. So for example, if your authentication data includes a username and password, those are sent in clear text between you and the proxy. So I really think that if you're building you appear to be building something that is useful over large networks, not inside private LANs. And whenever you're outside of a private LAN, TLS should be, or equivalent should be mandatory.
I see.
The other, the final thing I want to point out is that this use case is already served by proxies over HTTP, including all of the zero RTT functionality. So I think we should think very carefully about whether we want to duplicate the functionality of modern HTTP proxies or whether we want to basically invest in improvements to those proxies.
Yeah, I mainly have two comments to Ben. So the first one is that with Mptcp, there is already at least two deployments of using SOCKS solutions to do bonding of any type of access networks together through a SOCKS server. And one of them is public. That's the over-the-box solution from OVH in France. And they use shadow SOCKS with a solution where there is encryption on the different links. So this addresses the comment from Ben, and this is a solution which is SOCKS v5 with shadow SOCKS. It doesn't use TFO, but I guess if they could use your TFO code, they would be very happy to do that. So thanks for providing the code. And concerning the existence of HTTP proxies, this is nice. We have lots of HTTP proxies, but we have to remember that there are other traffics than HTTP. So we live in a world where there are other applications than HTTP. So we cannot only rely on HTTP proxies.
I definitely want to clarify that HTTP proxies include the entire TCP proxying functionality that we are talking about here in the form of HTTP Connect.
Julius Krobacek. I would also like to clarify that a normal human being cannot implement an HTTP proxy while obeying all the requirements of all the RFCs that are mandated by the RFCs.
Any more comments or anything? Anyone? Okay, so you're presenting this in Area later in the week? You haven't done so yet. Okay, great.
All right. So thank you for your time.
Thank you, Vlad. Thank you for bringing it to us. So that's great. We've reached the end of today's agenda. So Friday, when we're in a different room, in the, I think it's called the afternoon session, when Marcus will be talking about his robust session establishment proposal and Quentin talking about proposal for fast flow creation, and then there'll be some time if people have any more reactions to particularly to the proxy work that we've heard about today, and having had a think about it and read the drafts and stuff. So thank you very much to everybody for your contributions today. Thank you to Dave and Jing for doing the minutes. That's been great. And see you all on Friday.
HTTP2 supports proxy. Yes. So basically, you're doing some, and you're doing. I would be very interested in specifying a subset. If you wanted to specify a subset for HTTP graphics. Okay. 15 minutes. Yeah. Just fine. But it inherits a bunch of other properties.